Okay, now we are at the last problem. I would say this is a great problem, and it's not actually an easy one for eighth grader. But let's just have a look. So we've got a list of two-digit numbers, and I want to arrange them in such a way that the unit digit of each number matches the tenth digit of the number that follows. For example, 1, 2, and then it is 2, 3, and then 3, 1. So 1 is followed by a 1. 1 is followed by 1 and 4 and 4, 4 and 4, 5 and 5, so on and so forth, all the way to like 6 and 6. And the final number is 4, and the 4 doesn't have to overlap with anyone. And so the first number can be the unique one. The last number can be the unique one. However, in terms of number, the digits. The first digit and the last digit doesn't have much restrictions. However, all digits in the middle are kind of copied. Okay, so that's the idea. This is just a one successful arrangement. And the question is, how many such arrangements are of the given list of numbers are possible? Okay, so this is actually well, let's say we want to put numbers together so that you know, just look at this example. 1 to 2 and 2 to 3 and 3 goes back to 1, things like that. So we can, based on this, sort of create a directed graph. So what do I mean? So this is the thing. For example, let's look at the digits. We've got 1, 1. That is to say, if you start with 1, you can go to 1. So on this graph, we've got numbers here. We've got numbers here from 1. This is a digit 1. Okay, digit 1, because we've got 11, we can choose to move one step to ourselves. And this way, we end up with 1. So this edge, this step means we are doing 11. And we also have 12, which is 1, 2. So means from 1, we can go to 2. So from 1, maybe in the first step, according to this, no, not this one. Maybe in the first step, we just choose 12. That is, we go from 1 to 2. So we can go to 2, and then we can go to 2, and from 2 we can go somewhere else. For example, in this example, we go to 3. In fact 2 can go to 3, so we may choose to go to 3. So this is to say, we can kind of translate this list of numbers into a way of moving around in a graph. And what is the graph? So we have to study those numbers and digits one by one. From 1, we can go to 1. From 1, we can go to 2 and 4 as well. So we've got 1, 2. There's no 1, 3. Okay, 1 has got only 1, 2, 4. So 1, 1, 1, 2, and then 1, 4. 4 is over here, and then from 2 we've got 2, 3 only. So 2 goes to 3 only. This is the only edge connecting 2 and 3, and this is directed, so 2 to 3 instead of 3 to 2. And then we've got 3, 1, so 3 can go to 1, no more. So 3, 1 is the only edge. And then we've got 4, 4, meaning 4 has a, let's say, a loop, self loop. This is to say we can start with 4 and end up with 4. This is the number 44 if you choose to take this step. And then we've got 45 and 46. So we've got 2 more numbers, 2 more digits, 5 and 6. 4 goes to 5, 4 goes to 6. So far so good. And then we've got 5, 6, meaning 5 can go to 6. And then 6, 4. So 6 goes back to 4. Okay, we've got 2 different edges. 46 because we've got 46. 64, so we've got 64, 2 different edges, 2 different directions. And then we've got 6, 7, so 6 can go to 7. Finally, it's a 74, so 7 goes back to 4. Okay, so this is all information we have got regarding the numbers we have, regarding the steps we can take in this graph. And then we need to figure out a way such that we start from somewhere, and after some move, all edges has been traveled. All directed edges have been traveled in the specified direction, and there's no, let's say, repeating, because every number is going to be used once in the list. And the thing is that in this kind of a problems, just look at the incoming edges and the outcoming edges. For example, there actually isn't much choice with regard to 2, because there's only one incoming edge and one outcoming edge. Whatever you do before it and after it, 2 has to be done in this way. You start with 12, and then immediately after it you do 23. This is the only way you can do to put 2 to let's say put 12 and 23 in this list. That's the idea. However, for some numbers, it's not actually the case. For example, look at 1. 1 has got 1. Okay, there's an arrow coming in. There's an arrow coming in. So 1 has got 2 incoming edges, but it has got 1, 2, 3, 3 outcoming edges. That is to say, it's not paired. So 1 might be the very odd number, not in the sense of odd or even. I mean, 1 may be a strange number, the odd one out. So 1 should be the starting number, because the starting number goes out once, but this one receives no incoming edge. It's the starting number. So 1 should be the starting number. It has 3 outcoming edges, but only 2 incoming edges. So you're gonna start with 1. It could be 12, it could be 11, it could be 14. We never know, but at least 1 is the starting point. So I put a star beside it. And this is the starting point, and which is the ending point. In this case, the ending point is 4. Actually, if you look at this point 4, the vertex 4, you notice that it has 1, 2, 3, 4, 4 incoming arrows, 4 incoming edges. However, with regard to the outcoming edges, we've got 1, 2, 3 only. So it's 4 in and 3 out. That means at least once there's in without going out. If you go into some number without going out of it, that is to say, this is the end of the list. So the game is over. You don't have to go out. So 4 has to be the ending number. As for the ending number, I put another circle, the little star around it. So we've got a starting number and ending number. Okay, that's the basic plan. And also there's one thing. You realize that there are 2 parts. Almost there are 2 parts, and there's a kind of a bridge in between. And once you go over the bridge, there's no way back. That is to say, you must finish everything over here on the left-hand side, and then you take the bridge, you move to the right-hand side and do your job on the right-hand side. And so basically the idea is that you start with 1, finish everything over here, go across the bridge, and then you are at 4, then you do everything over here, and finally you should end up at 4. That's the, let's say, the very general plan. Okay, so we know we mark it by drawing a cut. So there's a cut, and we've got left and right. That's the idea. And then let's see. In this part, how many, because we want to know the total number of different arrangements. That is the total number of valid ways of walking around of traveling or walking around this graph. And since we said we should start with 1 and do the left-hand side, so how many ways are there to do the left-hand side? You realize that there is it's a cycle. It's a cycle, and there is a self loop. So you can do 1, 2, 3 first, and then do 1, 2, 1. Or you can do 1, 2, 1 first, and then you do 1, 2, 3. Only 2 choices. After you have done these 2 things, you have to walk over the bridge to the other side. So it's in total 2 ways here on the left-hand side. Okay, you can do the loop first and then the cycle, or you do the cycle first, then the loop. But once you are in the cycle, there's no way back. You must finish the cycle and then you do the loop, or you cycle first, the loop second. That's it. So 2 ways here, and this part is done. And now let's look at this part. This part it's more complicated. There is a loop. It can happen somewhere. Actually, the loop, is the easiest thing. once you're here, you just do the loop, it changes nothing. So maybe you can do loop anytime when you are at a vertex 4. But the things below here are a bit complicated. But as we said, you know, things like 5 and 7 are kind of okay because you don't have much choice, right? Once you are at 5, you must have gone from came from 4, and then you must go to 6 in the very next step. And the same for 7. If you're at 7, then I can tell you are from 6, and next you are going to 4. Okay, so actually the let's say the path 4, 5, 6 can be considered as one single path from 4 to 6, because 5 must happen somewhere in the middle. You don't have to worry about it. And the same for the path 6, 7, and 4. If you take this part, 7 must happen somewhere halfway. So it's actually a single path from 6 to 4. So that's the thing. We've got 4 here, we've got 6 here. So we've got this path from 4 to 6. This is path 1. Also, if you want to do 4 to 6, there's another path. This path is called 4, 5, 6. So this is actually 4, 5, 6. 5 is somewhere in the middle. We just write it here, indicating this is a different path. However, you don't need to take this number into consideration anymore. And for the same reason, from 6 to 4, you can take directly 6 to 4. So this is a path from 6 to 4, or you can go through, go via 7 before reaching 4. And this is called 6, 7, 4. 7 is somewhere in the middle, which you don't quite worry about. And then don't remember there's a loop here at 4. Okay, so this part, the right-hand part, is simplified this way. You start with 4 and you end up at 4. Okay, so the thing is that maybe because there are 2 ways from 4 to 6 and 2 ways back, so we need to take these ways back and forth, right? Go back and forth between 4 and 6. Maybe you move to 6, take one of the 2, and then take one of the 2 and go back. So let's call this A1 and A2. These are going out from 4 to 6, and for going back, we've got B1 and B2. And this loop, we call it C. Okay, so in this case, we can do these kind of things. You can do the loop first, and then you do A, B, A, B, because any A must be followed by a B. The loop is done, and without a loop, you must do A, B, A, B, right? You can do A doesn't make sense. If you're at 6, the next step you're going to take is a B something. If you're at 4, the next step you're going to take is a A something. So it must be C, A, B, A, B. Or you can do a pair of A, B first, whichever A, B you like. And then you are at 4 again, you do the loop, and then you do another AB. Or you can do both ABs and leave this C loop at the very last. So this is also fine, and that's everything you can do. So 3 different structures. You can do loop first, in the middle, or at the end. But AB must be done in such an order, and instead of AABB. And this is just a basic structure. For example, take this one, CABAB. You can choose. You can let them be A1, A2, or A2, A1. It doesn't matter. As for these 2 B's, they can be B1, B2, or B2, B1. So it is 2 times 2. In total, there are 4 different ways in terms of the specific step you take. You choose for A for each A and B. And for this, the same reason. It's a 4. There's only one C, but you've got 2 A's and 2 B's. You can choose freely. And this one has another 4. So in total, we've got 12 here. 12 ways to do the right hand side. For here, it's 12 ways. Let's write it here. 12 ways. Okay, it's 4 plus 4 plus 4. It's 12 ways. And on the left hand side, it's another 2 ways. And so in total, it should be the multiplicative principle. Okay, so times multiplication, 2 times 12, giving the answer, which is 24. And 24, fortunately, is one of the options you've got here. So the answer should be B. And the idea is that you'd better convert the whole thing. It doesn't matter. In theory, you can do everything without plotting the graph. But the graph can kind of visualize everything, gives you a better intuition of what strategy to use if you want to travel the list, if you want to travel the all digits, kind of arrange the numbers. So you get this graph and you need to analyze the graph a little bit, realizing it has two parts if we make a cut here. So the two parts can be done separately, and these kind of 5-7 things can be simplified. So you get this, and then you use your well-trained counting technique to get this number. Finally, it's a multiplicative principle giving the correct answer. I think that is it for everything, and that's it for this year, I think, and see you in the next year. Bye.